Welcome to the UW CSE Distinguished Lecture Series. It's my pleasure today to introduce Dan Boneh, professor at Stanford University. Dan is a leading researcher in computer security and cryptography. He's won a number of awards, including the ACM Infosys Prize in Computing, which is ACM's top award for a mid-career researcher, and the Gödel Prize for his work on bilinear maps and identity encryption and identity-based encryption. Please join me in welcoming Dan.
Great, thanks, Paul. This is fantastic. So it's really a pleasure to be here. You guys are so lucky. You have a wonderful, beautiful building, a beautiful campus. The faculty are fantastic. So it's really a pleasure to visit the university. So thanks for inviting me. I always enjoy my visits to UW. All right, so today I wanted to talk to you a little bit about basically how to build anonymous communication systems. So how to hide the metadata in communication systems. And I have to say the talk is more free-flowing, so feel free to interrupt with questions, or if you want to discuss anything in more detail, just let me know, and I'm happy to dive into anything in more detail. But before we talk about hiding the metadata in communication systems, I should say, by the way, this is joint work with my student, Henry Corrigan-Gibbs, and with my colleague, David Mazieres. Before we talk about communication systems, I did want to tell you about kind of a fun project that we did a while ago. This was joint work with a psychologist. It's a work that I've had a lot of fun doing. So I wanted to tell you quickly what it's about. So I wanted to show you how to build something called rubber hose resistant cryptography. So maybe folks in computer security have heard me speak about this, but since this is a talk for a broader audience, I wanted to quickly mention what the problem is. So I imagine many of you have seen this XKCD cartoon. In fact, it seems in the last couple of years, it seems like a lot of my research is driven by XKCD cartoons. It's like almost for anything I do, I can find the relevant XKCD cartoons. It's an amazing comic strip to read. So, so this basically talks about, the crypto nerd's dream, where, strong crypto protects our world. But in reality, of course, you can just beat somebody up and get the key from them, and then all security goes down the drain. So I should say, again, this work that I'm about to describe is joined with my student, Riposte, Daniel Sanchez at SRI, Paul Reber, who is a psychologist at Northwestern University. So it's been a lot of fun collaborating with a psychologist. I've been telling people that I work with a psychologist, and I've learned that I have to be careful when I say that, because they interpret it the wrong way. And then Pat Lincoln, who is at SRI. So again, I highly recommend it to you to maybe reach out to the psychology department here. There's a lot that we can collaborate on and teach each other about our respective fields. So what is rubber hose resistant crypto? So the problem I want to tell you about is this question of authenticating someone at the entrance to a secure facility. So think of someone walking into the Pentagon or walking into the NSA, and the guard wants to authenticate that this is really a Pentagon employee. So how do you do it? Well, so you can give an employee smart cards, and then the employee uses a smart card to authenticate themselves. But of course, smart cards can be lost or stolen, so that's not a perfectly secure way to do things. You can authenticate them based on their biometric, right? Their fingerprint, their retina scan. But if any of you have watched James Bond movies, you know that, or Mission Impossible movies, you know that biometrics are actually not particularly secure. In fact, there are lots of YouTube videos that explain how to bypass biometrics. In fact, here you have examples of these gummy fingers that are typically used to defeat biometric systems. So that's not perfectly secure either. The problem with passwords, of course, is that I can not me, but someone can beat the person up and get the password out, maybe threaten their family, and then employees will give up their password. In fact, there's a study that shows that if you just offer someone a piece of chocolate, they'll be happy to give you their password. So passwords are quite problematic. And the question is, can we do better? So is there basically a better credential that we can use that's not as easily extractable from the person that's holding it? So let me show you what we proposed. But before I do that, I have to tell you a little bit about how the brain works. So this is where the the interaction with psychology comes in. So when you look at the human memory system, there are basically two components to it. There's what's called the hippocampus and the basal ganglia. So the hippocampus is everything that we know is stored in the hippocampus. Basically, This is what we call conscious learning. So when I read a paper and I learn the formulas in the paper, those formulas are stored in my hippocampus. In fact, humans have an enlarged hippocampus compared to other mammals, and that's what makes us unique. On the other hand, the basal ganglia is sometimes what's called muscle memory. These are things that when I learn how to ride a bicycle, how to ride the bicycle, that knowledge is stored in the basal ganglia. The basal ganglia works very differently from the hippocampus. It learns from repeated examples. So it sees examples over and over and over and over again, and finally it figures out what it is that it needs to know. So this is why when you learn to ride a bicycle, you try it over and over and over and over, and then finally you figure out how to do it. So when you play tennis, right, the way to make the shot perfectly, that's all stored in the basal ganglia. And in fact, the basal ganglia is designed to be not consciously accessible to us. So knowledge in it is not something we can explain. We can't explain how we ride a bicycle. And in fact, like there's this classic story about golfers, right? So the way you hit a perfect golf shot, that actually is, again, you try it again and again and again and again, and that information is then stored in the basal ganglia. If you want to mess up a golfer, you kind of ask him, think about how you're making the shot as you're making it, and they'll mess up the shot. Because the minute they start thinking about how they're doing it, it's the hippocampus that's controlling your muscles, and that is not where the knowledge is stored. So the interesting thing is, again, knowledge in the hippocampus is accessible to us. Knowledge in the consciously accessible to us. Knowledge in the basal ganglia is not consciously accessible to us. Aha, so that's an interesting place where we might try to put an authentication credential. So what we were trying to do is basically use this technique called implicit learning, where we can train the basal ganglia to know something in a way that the hippocampus doesn't pick it up. Okay, so we give lots of examples over and over. The basal ganglia picks up the pattern and learns it, but the hippocampus cannot. And as a result, now it's a way for us to implant a piece of knowledge in your brain which you do not have conscious access to. So even if I beat you up and I threaten your family, there's nothing you can do to give me that piece of knowledge, because you know it, but you don't know that you know it. Yeah, it's kind of a Rumsfeld thing. Okay, so so the credential is effectively not consciously accessible. So let me show you how we do it. So the way we implant a secret in your brain in the basal ganglia is through a game. And the game operates as follows. So essentially, well, you have to agree to the experiment first. And then basically there are these balls that fall down these slits. And every time a ball reaches the bottom, the player is supposed to hit the corresponding key, S, D, F, J, K, L, on the keyboard. And so, your goal is basically to hit the keys as the balls come down. So, right, so you see a D, then an S, then a K. And you do this over and over and over again. But in this sequence of balls, there's an embedded sequence of 30 characters. Yeah, 30 characters is a little too much for the hippocampus to pick up, but the basal ganglia is very good at storing these long sequences of patterns. Maybe I should give another example. When you learn to play a piano piece, the reason piano players play the piece over and over and over again is they're trying to get the piece into the basal ganglia. That's why you have to play it over and over and over until you get good at it. And the fact is, it's able to keep these long sequences, in particular here of 30 balls. And as you learn the sequence, you get better at playing the game. So you can kind of anticipate what the next ball is going to be, and so you can actually press the correct key faster. So over time we make the balls fall faster and faster and faster, and that actually is how. And the fact that you're still able to keep up means that your basal ganglia actually learned the sequence. Now the amazing thing is, the experiment is to train people with this sequence, and then you ask them, can you identify what it is that you learned? And again, the sequence is actually nice combinatorics that went into designing these sequences, which I won't get into here, but I'm happy to do after the fact. Actually, nice mathematics about Euler tors and such in designing sequences that will not be picked up by the hippocampus. And you ask them, tell us which of the 5 sequences you learned, and they have no idea. Right? Literally, the graph that comes back is a flat graph showing that they have no idea what they just learned. So it's an example of how we can implant something in your brain without you knowing what it is that we implanted. And now, obviously, when we want to authenticate you, what we do is we basically make you play the game. So we show you a random sequence, and then we show you the correct sequence, and we measure the differences in your performance. And if you know the secrets, then you'll do much better on the correct sequence than you do on the random sequence. And that's how we can authenticate you. Yeah, so that's kind of the rough idea. There's a lot more to say about this, but I just wanted you to kind of be aware of this. This is a really nice interaction between computer security and psychology, so this is a lot of fun to do. I have to say, this also raises a lot of interesting open problems. So there's lots more to do here, and in particular, instead of just embedding like a fixed secret in your brain, which kind of acts as a password, it's just a password that's not accessible to you consciously. So instead of embedding a fixed sequence, it'd be nice if we could embed an algorithm in your brain. And if we could embed an algorithm, that would allow us to do something called challenge response, where I give you a challenge, a random challenge, and you can compute the response just using the basal ganglia. So this raises this really interesting question of, can we actually embed a challenge response algorithm into the basal ganglia? And so the first question is, how does it actually represent knowledge? And that we actually have a good guess as to how that works. Basically, it looks at we think it stores conditional probabilities. So given the last 3 or 4 balls, the next ball is likely to be such and such. And it actually does that over long sequences of balls. So we kind of have a good guess of how it represents knowledge. And the real question is, can we use it for cryptographic purposes, which is what we would need for challenge response? So can we embed a one-way function in the basal ganglia? And it sounds like the answer to that actually is no. So unfortunately, we probably can't do challenge response using this mechanism. But I don't know, maybe one of you will come up with a clever way of using a mechanism like this, and maybe we can do other forms of strong authentication. So I just wanted you to know about this work. I think there's a lot more work to be done here. And the main message is, interaction with other disciplines is really rewarding and a lot of fun to do. Question, yeah?
Your rubber hose, do they get worse at playing this game?
Oh, that's a good question. Yeah.
Different in that scenario from a...
Yeah, so if you beat someone with a rubber hose, do they get worse at playing the game? Well, so when someone kidnaps you and tries to, ties you to a chair and tries to extract the secret from you, all they can do is they can try to make you play the game. But they don't know the secret, so they don't know what sequences to show you. And as a result, they can't make you, it's kind of not clear how they extract the secret from you. What's even worse, if they show you lots of sequences, eventually it wipes out the secret that's already embedded in your brain. Yeah, so because you play the game over and over, and then you learn their pattern and forget the secret that you already knew. Yeah, so it's kind of interesting that it's got this self-destruct mechanism built into it. Yeah. So anyhow, this is not something that you would deploy tomorrow, because I can tell you it takes us like half an hour to train a user, and then it takes us about a couple of minutes to actually do authentication. So it's not something you can use right away. But again, it's a wonderful area for further research. Maybe using clever EEGs, maybe there's a way to speed up authentication. So lots more work to do here. OK, so this was just an aside. I just wanted you to be aware of this. Now that we've done that, let's go back to our main program. OK, so what I want to tell you about is this question of how to hide metadata in communication systems. OK, so how do we communicate without revealing who we're communicating with? So it's really fantastic for me to see, as a cryptographer, it's wonderful for me to see that all of a sudden there's lots of options for secure communication systems. There are lots of applications out there that use end-to-end cryptography to protect messages. So Signal, WhatsApp, iMessage, Wire, all these systems encrypt messages from Alice to Bob. And the service provider doesn't see any of the contents of the messages. But the point to remember is it protects messages. It does not protect your metadata. Okay? So who you're talking to is actually not protected. So what is metadata? What is this metadata that we're so worried about? Well, so for example, if Bob calls the AIDS clinic, the metadata will say, here, Bob called the AIDS clinic at this and that time, and they talked for this long, and here's the amount of traffic that was sent. So, that might reveal something sensitive about Bob. Or you can imagine, if the CEO of Yahoo calls the CEO of Verizon, that might say, oh, there's some deal brewing that could, affect the stock market. So again, these are very important things that leak just by the fact that the call was actually made. So metadata typically is actually not being protected, and in fact, I can tell you that if you look at like the WhatsApp terms of service, so again, WhatsApp, a very popular chat system. I imagine many of you actually use it. If you look at their terms of service, they say very clearly, we collect service-related diagnostics, blah, 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 in particular, how you interact with others using our services. So they actually tell you explicitly that they are collecting and storing metadata. In fact, of the systems I showed, three of the four systems I showed seem to be collecting metadata. Signal says that they're discarding metadata as it's collected, but again, the technology they use itself does not hide metadata. It's just that, of course, they're not storing it. So the question is, can we? Oh, by the way, I should say even Snowden actually commented on this question of metadata. So are your readers having trouble understanding the term metadata? And his suggestion is, instead of metadata, call it activity records. Maybe that will clarify to people more what we mean by this. So the question that we're asking is, basically, can we build these end-to-end secure systems that make it harder so that basically hide metadata from the service provider as well as hiding the content? Now, there's a bigger issue here. There's a kind of I guess, sort of a political issue around this question of metadata. And that's this question of, I should say security versus security. But really, the question of the world we're kind of converging to is a world in which everybody has access to end-to-end encryption, right? All these applications are available to us to do encryption. It's very difficult to put the genie back in the bottle at this point. Not that we would want to. But we seem to be converging on this status quo where content maybe is not available to law enforcement and maybe other governments, but metadata would continue to be available, right? That's kind of the thinking, that metadata will always be available to law enforcement. And I guess one of the points I'd like to make in this talk is that that's kind of not quite a stable status quo. If we really, as we hear of more and more abuses of metadata, actually, there are ways to build systems that hide metadata as well. So thinking that, the compromise will be content is encrypted when metadata is in the clear, that's not clear that that's a stable status quo, right? We actually can design systems that scale and work at internet scales and hide metadata. And I want to show you some ways in which that can be done. So there's even somewhat of a political message here as well. All right. So the first question you should ask me is, well, we already have systems that provide anonymity. What's the classic system that provides anonymity? Tor. Yeah, exactly. So why not use Tor? So Tor, Tor is a fantastic system. It's very widely deployed, big success in terms of protecting who's talking to who on the internet. However, it is useful to remember that Tor is designed for performance. So they'd like you to be able to watch video over Tor. And because it's designed for performance, they did have to make some compromises on the level of anonymity that it provides. In particular, if you have a global adversary that could do traffic analysis on a lot of Tor nodes, it's actually fairly acceptable now that with global traffic analysis, you actually can undo some of the anonymity that's provided by Tor. So that's one issue. Then there's another mechanism for providing anonymity called mixnets, which I'm going to talk about in just a minute. But mixnets generally actually do require some sort of expensive operation, known as a zero-knowledge mechanism. Again, I'm going to explain why that's necessary in a second. And what I'd like to show you in this talk, I think it's kind of a fun mechanism, is this new system called Riposte. That provides, again, anonymity. It's an anonymity mechanism that protects against traffic analysis. So a global adversary is not going to be able to break anonymity using traffic analysis. And what's kind of interesting here is it actually does scale to fairly large anonymity sets for as long as the messages are not very large. So it's actually not designed for video. It's more designed like a Twitter system. So if you're a Twitter in Syria and you want to tweet about what's happening in Syria, then this will be a system that will allow you to do it with anonymity, where the anonymity set is actually very, very large, like millions of users. That's our goal. Okay, so I think it's kind of a fun mechanism, actually. So this is why I chose to speak about this, because it's kind of a way to provide anonymity without mixing. Traditionally, we always think about mixing as a way to do anonymity, and this is a different way to do it. Okay, so let's talk about mixnets for just a second. So again, I hope many of you have heard of mixnets before. If you hadn't heard of mixnets, let me quickly explain how they work. So the idea behind a mixed net is that if I want to send a message to a remote server, I don't send the message directly. Instead, what I do is I find a number of proxies that will proxy the message for me. Let's say in this case, I find 3 proxies. And the only assumption I make is that these 3 proxies don't all collude together. In other words, one of the 3 proxies is honestly following the protocol and not colluding with the other 2 proxies. And the way a mixed net works is basically I take my message, maybe I'm M1. So I take my message and I combine it with a message of a bunch of other people. So everybody sends their messages to the first mix. So we have these 4 messages here. But when I send my message, what I do is I encrypt it using, let's see, the outer layer, this blue outer layer, is encrypted using the public key of the first mix. The green layer is an encryption using the public key of the second mix. And the inner layer is an encryption using the public key of the third mix. Okay, so I'm creating this nested encryption. This is sometimes called an onion encryption, which you'll see why in just a second. And then all 4 users do the same thing. So everybody sends these onions to the first mix. What the first mix does is it basically strips out the first layer of encryption and permutes and outputs the result. Okay, so that's the first layer of mixing. And you can see that because we decrypted and permuted, it's not possible to actually relate the outputs to the inputs in a way that you can recover the permutation. So the permutation that the mixed-net did here remains secret. An observer can't figure out what that permutation is. Then the second mix is going to do the same thing. It's going to strip out one layer of encryption and permute. And then finally, the third mixed-net is going to strip out the last layer of encryption and permute again. And now you have a list of messages. And if at least one of these servers is not colluding with the other servers, there's no way to tell which user sent which message. Yeah, so that's the idea behind the mixed-net, and that's actually relevant to how Tor works. The problem with this basic idea is that it's insecure once one of the mixes is an active attacker. Okay, so let's pretend, for example, the first mix is malicious, and it's trying to figure out who said, right, so it wants to know who sent the message M1. Yeah, so it wants to know, it sees the message M1 in the output, and it wants to know who sent that message. What it could do, or rather it could say it wants to know what the first user is saying. That's what it wants to know, what the first user is saying. So what a malicious attacker could do is that basically when it produces its output, it does the right thing on the first user's input. So it strips out the blue layer and places that in a random location. But then it discards all the other inputs and just puts encryptions of junk on the other inputs. Okay, so now you can kind of see what's going to happen next. The second mix does its job. It permutes and strips. The third mix is then going to do its job. It permutes and strips. But now, lo and behold, you see junk in M1, and now the first mix learned what the first user was saying. It learned that the first user was saying M1. So the first user now has no privacy. Okay, so again, it's important to remember mixed nets by themselves, if you just do the mixing, that actually does not provide security against a malicious mix. So what's the solution to this? The traditional solution to this is basically, well, let's make every mixer prove that it did the permutation correctly. So what the mixer does is it outputs what's called a zero-knowledge proof to say that the output is actually a permutation and a decryption of the input. Right? And every mixer has to do that. And so if all these proofs actually verify, then you know that this malicious attacker, this malicious mixer attack is not going to work. All right? That's kind of the idea in how you protect against malicious mixers. Of course, the problem now is you got to run these zero-knowledge proofs, and they're not that cheap. I should say there's actually the best proof of, this is called a proof of a shuffle. Right? So you want to prove that you shuffled correctly without changing the actual inputs. And so the best proof today is due to Bayer and Groth. And the point there is that it's actually, the work per mix is kind of linear in the size of the anonymity set. So I want you to remember this. It's the more people send their messages to the mixer, the more work has to be done in proving that the mixer is doing its jobs correctly. If you don't do that, then you're vulnerable to active attacks. Although I should say there are other designs for mixed nets. There's this really beautiful work called Vuvuzela and Stadium. These are other designs for mixed nets that actually try to avoid some of these mechanisms. Okay, So that's kind of what's been traditionally done in the area of anonymity using mixing. I want to show you now a way to do mixing to provide anonymity without mixing. Okay? So pay attention. This is kind of getting to the point of what I want to talk about. So how do we provide anonymity without mixing? So a completely different approach. It's inspired by these things called dining cryptographers nets and writable peer. But I can explain kind of the Strawman idea very simply. So here's the Strawman scheme. This scheme actually, you would never use it in practice. And in fact, it's a challenge for you to figure out what's wrong with the scheme. And I'll show you. If you can't figure it out, I'll show you. And then we'll fix it. We'll fix each objection until finally we get a system that we actually can use in practice. OK, so what's the Strawman proposal? So remember, just like in a mixed net, we had to assume we had these 3 proxies, that at least one of them is honest. We're going to do the same thing here. Let's start with the case of 2 mixers or 2 anonymity servers where the assumption is that they don't both collude. So one of them could be completely malicious, but the other one should be honest. OK, so that's our assumption. So non-colluding servers. All right, so here we have non-colluding servers. So now how do we provide anonymity? So imagine Alice wants to write a message M. So so we're going to assume M lives in some field. That doesn't matter so much. Basically, it's just a number. She wants to write a number that she later on will be published, but no one can tie that number back to her. So what does she do? All right, so here we're getting to the punchline. All right, so the first thing she does is she's going to choose a random place in this database. You see, each server maintains this database that has 5 entries in it. So Alice will choose a random position in the database. Let's say she chose position number 3. Now, what she's going to do is she's going to build a vector that has zeros everywhere, except the 3rd position is going to be her message. And now she's going to do what's called secret sharing on this vector. So she's going to choose another random vector, completely random vector. I should say these R's are in this finite field, so it should be clear to you how we choose. We're choosing random values from a finite set, so nothing fancy there about choosing random values. Okay, so she's going to choose this other random vector, and then she's going to subtract the 2 and get a 3rd vector. So these 2 vectors here, this random vector and this subtracted vector, this is what's called a secret sharing of the vector that we started with. You notice that if you look at the random vector, of course, that reveals nothing about Alice's message. And if you look at the second vector, just the second vector by itself, it's just a bunch of random numbers. Yeah, so it also reveals nothing about the message that Alice is writing. And then she's going to send one vector to one server and another vector to the other server. Okay, so she sends them to the servers. And the servers, all they do, no zero-knowledge proofs, all they do is they just add the value in to their current accumulators. Okay, that's it. And now, again, if you look at what server number 1 learned, well, he learned nothing. He just sees random numbers. If you look at what server number 2 learns, he also learns nothing. All he sees is just random numbers. This R3 plus MA is just a random value in the field that the message is chosen in. All right, so that's step number 1. So now Bob comes along, and he wants to write a message as well. So what he will do is he's going to choose a random position. Let's say he chose position number 5. And now he's going to do exactly the same thing. So he's going to generate a random vector and produce the difference. And he's going to send each one of these vectors to each one of the servers. So here he's sending the vectors to each one of the servers. And all the servers do, all they do is they just add the values in. And that's it. Yeah, very, very little work for the servers. And again, you see the server learns nothing about what Bob says and nothing about what Alice says. And then Charlie comes along, and David comes along, and Eve comes along, and each one of them writes in exactly this way until an epoch is over, until the end of the epoch. Let's say that the epoch is like 1 minute. Now, if you're thinking about a Twitter system, in 1 minute you get a couple of hundred thousands of tweets, maybe even millions of tweets, right? So we collect like millions of tweets like this. And at the end of the epoch, what do these 2 servers do? Can anyone guess? Yeah, actually what the 2 servers do is basically this is when at the end of the epoch, at the end of the minute, they get together, right? So here, they get together, and they simply add their values, and lo and behold, you can just do the arithmetic, and what comes out is basically the messages that the users were sending. So here, Alice's message comes out, Bob's message comes out, but nobody knows who tweeted what, right? So if you have 1 million users here, you'll get 1 million messages, but you have no idea who tweeted which message. All right, so this is a way to provide anonymity or privacy without actually revealing without any mixing. Yeah, we didn't mix anything. We kind of just wrote, the clients kind of just wrote to the different servers, and at the end of the epoch, the the anonymity is preserved. All right. So that's kind of the basic strawman scheme. This doesn't work for a lot of different reasons, and I imagine you are already starting to think about all sorts of objections in your head why this doesn't work. Okay, so let's walk through the different objections and see how we address each of them. Actually, before that, let's look at properties of the scheme. So first of all, the scheme has actually, it has I'll put it in quotes, perfect anonymity. We define all this in the paper. But in the sense that as long as the servers aren't colluding, as long as one of the servers is honest, really you have no idea who tweeted what, right? You kind of have this privacy that's preserved as long as the servers don't collude. In fact, if you don't like the idea of two servers, right? Maybe you're worried that these two servers might collude. You can actually blow it up to k servers, and as long as one of the servers does not collude with the other k-1, you'll have anonymity as well. Yes, it's a pretty strong anonymity guarantee. So that's one property that's nice to have. The other property is you realize this, like, the servers are doing nothing. All they're doing is just computing additions. So as far as work on the servers, it's very, very little work. They're not doing any decryptions or anything. They're just doing these simple additions. And the third property is what's interesting. Yeah, so this is kind of I think the key selling point of a system like this, which is the anonymity set. The set of people that you're entangled with, actually can be a lot larger than just the people who are writing. In fact, you can imagine that anyone who's reading the system, anyone who's just using the system to get information, just by reading, they could also just write a 0, right? So you can imagine writing a 0. That just means generate two vectors generate two random vectors that sum up to 0. Send the two vectors to the two servers, and now you are part of the anonymity set, even though you didn't write anything. Yeah. So by writing 0, you can be part of the anonymity set without actually costing anything to the system, right? So in a mixnet, the larger the anonymity set, the harder the mixers have to work. Whereas here, you could have an anonymity set that's much larger than a set of writers, and it's effectively free. You're not increasing the storage requirement at all. Yeah, that's kind of a nice feature of this mechanism. So I want you to remember that this is a nice benefit. That essentially, when you implement this, it's not just the writers who are writing to these servers. Readers also write to the servers, and they're kind of artificially increasing the anonymity set without any adding extra complexity. Okay, so there are lots of problems with the system. So let's try and fix them one by one. So the first complaint is, you remember I said we're expecting like 1 million people to be writing to these servers, right? So we want a very, very large anonymity set, so lots of people writing. So that means that the databases themselves, right, the servers, the two servers X and Y, they have to have relatively large databases. Like the database is going to have to be of size 1 million if we're going to handle 1 million messages. So that says that each one of the users is going to have to send very large messages. So if there are n users in the system, each user is going to have to send a message proportional to n. So again, if n is 1 million, each cell phone that's writing is going to have to send megabytes to each one of the servers. So that's not really practical. Turns out there's a very beautiful solution to this using what's called a distributed point function. So I want to show you what a distributed point function is. I have to say this was developed over a sequence of papers by Shor and Gilboa and Yishai, and then latest is Boyle, Gilboa, and Yishai. This is absolutely beautiful, beautiful work that fits our problem perfectly. And so let me explain to you what is a distributed point function. I think it's a good thing to know, as I hope it might actually be relevant in your research as well. So what is a distributed point function? It's basically a way to take these vectors and compress them to very, very little information. Okay, so instead of sending the vectors as they are to the servers, instead, what Alice is going to do is she's going to say, she's going to run locally an algorithm, which I'll call the generation algorithm, which says, I want to write the message M into position number 3. Okay, so the generation algorithm is going to output 2 keys, a left key and a right key, okay, KL and KR. Now, these keys are going to be relatively short, and she can send them over to these servers. So here, she sends them to the servers. And what the servers do with these keys is, by themselves, they can compute the entire vector that she would have sent otherwise. So let's see, the left server takes the key KL and can expand it into the vector that Alice would have sent in the first place. And same thing for the right server. So you notice the property here is that the sum of these two vectors is 0 everywhere except for one point. And these vectors are derived from the key KL and KR. The security property should be that given the key KL, you cannot tell what the point is, right? So you cannot tell that the point here is position 3. Again, this is a point function because it's 0 everywhere except at position 3. So given KL, you should not be able to tell what the point is, and given KR, you should not be able to tell what the point is. That's the property that we'd like to preserve, all right? And the amazing thing is that we can actually, so by the way, this is why it's called a distributed point function, right? We are taking a point function and splitting it up into two halves, but the halves themselves are very short. So the keys KL and KR are much shorter than the size of the database. All right, so the reason, so this is kind of the mechanism. I think it's a good mechanism to know that it exists. And the point is, I should say, by the way, we're able to get the performance we're getting thanks to Intel. So Intel actually, one of the things they did recently is they implemented the AES block cipher in hardware. And so they added these new instructions to the processor called AES. NI stands for AES new instructions, which actually implement AES extremely fast. Yeah. So if anyone ever tells you that block ciphers are slow, tell them that they're wrong, because Intel actually added hardware support for AES, and now you can actually make AES run essentially as fast as you can read from memory. So it's basically encryption has become free. It's another reason, by the way, why the world is moving towards encryption everywhere, because there's no longer performance bottlenecks to using encryption. Okay, so the reason why we're able to make this thing work is because at the performance that we're getting is thanks to these Intel instructions. Now, in our case, we just chose to use a very simple distributed point function where the length of these keys is proportional to the square root of n as opposed to linear in n. Okay, so in the case of 1 million users, yes, we go from megabytes, which is what we would have to do if we were doing it naively, to kilobytes, which is what we get from the system. So if you're tweeting, basically you're sending, 160 characters, so 160 bytes times the square root of 1 million, which is 160 kilobytes, which is nothing, basically, for a small device. So that was enough for us. But if we wanted to, we can even reduce this to logarithmic in n, log n, at the cost of a bit more work on the servers. But we just decided not to do it because for 1 million, this square root of n is sufficient for our purposes. Okay, so maybe if I have, it looks like I have a few minutes. Why don't I show you actually how these distributed point functions work? Again, it's a really, really clever construction. And so let me show you, again, this is due to as I said, Shor and Gilboa. So let me show you how these work. This picture actually captures the whole thing. So remember, our goal is basically to build these two keys that together, that every server can evaluate on its own and build, the vector on its own, such that the sum of the vectors is a point function. But without learning the servers on themselves, they learn nothing about where the point is. That's our goal. So here's how it works. So the keys are going to be made up of, there's a binary vector, a vector of seeds, which I'll explain in a second, and another correction vector. Okay, so those are the two keys. So the right server has a binary vector, a vector of seeds, and a correction vector. And those are the things that are going to be of size square root of n. Now, so we're going to have to use what's called a pseudorandom generator. So this is something that takes a short seed and expands it out to a pseudorandom output. Okay, so in particular, we're going to generate square root of n elements in the field that we're working in. So by the way, whenever you hear the number whenever you hear of square root of n, you immediately think of squares, right? And in fact, that's what we're going to do here. We're going to break things up into squares. So the structure is going to look as follows. So say we're trying to hide the message in this position in the square. So you notice everything is 0, except this one entry is the value m. This is why it's a point function. And so let's see how we do it. Basically, the binary vectors, the two binary vectors BL and BR are identical, except that you see in position 4, in the 4th row, I guess we start at 0. So if we start at 0, it'll be the 3rd row. You notice these vectors, one vector has a 1 in it, and the other vector has a 0 in it. Yeah, so the vectors are the same, except at one place they're complements of one another. And similarly, the seeds are the same everywhere, except that in the fourth row, the seed is different. There's one seed on one side and a different seed on the other side. So actually, these are going to be the keys, right? So the keys, if you notice, the keys are BL, SL, and V. And that's one key, and the other key is BR, SR, and V as well. So let me show you what the servers actually do with these keys. So you take the seed S0 and you run it through this generator, and that gives you basically one row's worth of randomness. And now you either XOR the correction vector or not, depending on whether the bit is 1 or 0. So if the bit is 1, you XOR V. If the bit is 0, you don't XOR V. And you do that throughout all the elements. So that's what the left server does. The right server does exactly the same thing. He evaluates the generator at all the seeds that he was given. If the bit is 1, if the corresponding bit is 1, he adds V. If the corresponding bit is 0, he does not add V. Yeah, very simple operation. And now look what happens. If we look at the first row, you notice we have the same values for both the left server and the right server. So when we XOR the two together, we get a row of zeros. So that's good. That's what we wanted. So all the rows are going to be 0 except the critical row, the row that contains the message M. What happens at the critical row? Well, at the critical row, you realize one bit is 1 and the other bit is 0. So on the left side, we're going to XOR by V, and on the right side, we're not going to XOR by V. So when we XOR these critical rows together, what we're going to get is GS3 XOR GS3 star XOR V. Yes? So all we do is set the correction vector V to be, cancel GS3, cancel GS3 star, and then give me M times the unit vector at 4. All right, so you can see that when you add these two values together, you're gonna get a 0 vector that's simply set to M at the right position. And why is this private? Well, if you only get to see these guys, the vector BL is just a random binary vector. The vector SL is just a random vector of seeds, and the vector V, you notice, is actually blinded by this thing. Actually, could reveal what the message is, but it's blinded by a seed that you don't know. So the left guy knows S3, but he doesn't know S3 star. So the message is blinded. The right guy knows S3 star, but he doesn't know S3. So again, the message is blinded. This is a pretty cool construction, I have to say. This is really, 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 really nice. And basically, to get this down to logarithmic, you just have to rebalance the square. Yeah, so there's a recursive construction that makes this even smaller. Yeah, so I hope this was clear. It's kind of a useful primitive to know in general, right? That you can take these vectors, you can take a point function, distribute it, and compress the keys to generate the point function, and still have privacy. All right, so this is basically how we avoid the issue of bandwidth. Okay, the next issue, the next problem. So remember, your challenge was to think of the different problems with the scheme. Yeah, so I'm sure you're thinking, actually, does anybody want to propose a problem? What problem should we look at next? Can you think of another? Yeah.
What if two users write messages to the same row?
Awesome. Exactly. Thank you very much. That's a great question to ask. Let me get to that in just 1 second. Let me do the problems the order. Let me do the problems in the order that I wanted to do them. And the next one we'll deal with collisions. So the second problem I want to deal with is what happens if 1 million people write, but one of these 1 million people decides to ruin it for everybody else. Yes? What that one person could do, here, let's say this is Bob, he could just contribute complete noise, complete garbage to both servers. And you realize if he does that, then basically he kind of wiped out all the information in both servers, and when they add things up at the end, they're just going to get random junk. Yeah, so one user can mess everything up for everybody else. So that's really bad. That's not a good system to have. Well, so our solution to this, actually, this is a big chunk of the paper. I'm going to skip over it. Our solution basically to this is there's like an auditor that lets you test that, in fact, nobody can do this. Yeah, so there's an easy way to get around that and make sure that the system is actually robust. But let me skip over that in the interest of time. The third problem is collisions. And so here I also want to teach you a trick that hopefully will be useful to you in other contexts. So what's the problem with collisions? I'm sure you already see this. So Alice writes to slot number 3. So here's R3 and minus R3 plus M. And then Bob comes along, and he also writes to slot 3. So then when we combine the two servers, we get the sum of MA plus B, and now the messages are lost. Yeah, so that's not good. So if there's ever a collision, we lose. So the obvious way to deal with collisions is what? What? Yeah, make a big table, right? So if you can make the table big enough, so if you have a table, let's see, if you have n users and the table is of size n squared, then you're not going to have collisions by the birthday paradox, the birthday bound. Yeah. So if you have 10 to the 6 users, well, that means the table is going to have to be of size 10 to the 12. So that's not great. That's a really big table. So that doesn't work. So don't do this. Don't do this. But it turns out there's a much better solution using coding. And so let me show you a cute trick to avoid collisions that, like I said, hopefully will come up in your work as well. So let's pretend for a minute that the table is of such size that maybe two-way collisions can happen, three-way collisions can happen, four-way collisions can happen, but the probability of a five-way collision, that 5 people chose exactly the same slot, let's pretend for a minute that that happens with low probability. Okay, and 5 is a parameter. You can make it as small or as large as you like. Well, if that's the case, let me show you how to recover from collisions. So what we'll do is we'll make the table a little bit wider. Yeah, so when Alice writes her message, she's not just going to write m plus r, but in fact she's going to write m squared, m cubed, and m to the 4th. Okay, so when she writes her message, she actually writes 4 elements to the table. Yeah, that's all we do. Now when Bob comes along and he collides with Alice, now he's going to do the same thing. So we're going to get ma plus mb, ma squared plus mb squared, ma cubed plus mb cubed, and so on and so forth. All right, so each one just writes 4 elements to the table instead of just writing 1. Now what happens when what happens when we get to the end of the epoch and we collect all the results? Well, when we add up the right server and the left server, you notice what we'll end up with is there's a 4-way collision, so we get the sum of the 4 messages, just like before, but we also get the sum of the squares of all 4 messages, and the sum of the cubes, and the sum of the 4th powers of all 4 messages. So we end up with a system like this, system of equations like this. And you realize we have 4 variables, ma, mb, mc, and md, and we have 4 equations. They're not linear equations, but they're 4 equations. So presumably, there's not too many solutions to this. And the simple way to solve this, this is a system that turns out to be really easy to solve. The way you solve a system like this is basically using a trick called the Newton relations. So the Newton relations let you translate from these kind of polynomials to the symmetric polynomials. But the point is, using the Newton relations, you can basically recover the coefficients of the polynomial f, whose roots are ma, mb, mc, and md. Okay, again, a very good trick to know, that these sums of different powers will let you convert back and recover the coefficients of a polynomial that contains these roots. And now you just factor the polynomial. You just find the roots of the polynomial. And you find the messages ma, mb, mc, and md. But the beauty of this is you don't learn who wrote what. You just learn the messages, but you have no idea who inserted what. Yeah. So this is kind of a good trick to keep in mind. It's a general way of avoiding collisions in a problem like this. All right. Okay. Good. So basically, this kind of as an outline for how we solve the various problems in the system. So of course, we have an implementation of this. It's implemented in Go. This is Henry did the implementation. And then you can see that basically, to handle something like 60,000 users, because of, as I said, all the optimizations that go into this, we can handle something like 30 writes per second on just a single dinky laptop. This is not even a server. It's just his MacBook. Just his MacBook can already handle 30 writes per second. You can imagine that on a server, multi-core, and so on, you can handle much more. Twitter, by the way, the rate of tweets at Twitter is about 5,000 tweets a second. 5,000 per second. I guess they have one famous user, but he's only one of those 5,000 a second. Right, so 5,000 a second, which means that basically, using roughly 100 machines, you can pretty much handle all of Twitter. Yeah, so that's nothing. That's perfectly reasonable. Everything is completely parallelizable. The servers, all they're doing is they're just adding these values. So definitely, you can run this on multiple machines. So I have to have a graph. Can't give a talk without a graph. And so let me show you what this graph means. So here we have the top red line basically indicates the number of TLS sessions, the maximum number of TLS sessions you can do to a single machine. And the yellow line here is the maximum number of AES operations you can do on a single machine. So you can see that when the number of users is relatively small, like if there are only 100 users in the system, then we're dominated by the time to do TLS. Yeah, the computation is free, and we're dominated by network performance. As the number of users increases, like for example, when we have 1 million users, you can see that the bottleneck is actually the rate of AES. So the faster AES is, the more users we can handle. And here the news, it's very important to remember that actually AES-NI was extremely successful for Intel. It was a good differentiator for them. And so they're making AES-NI faster and faster and faster as time goes by. So it started, just so you know the history, it started taking 7 milliseconds per round of AES, sorry, 7 cycles per round of AES. Then it went in Skylake, it went down to 4 cycles per AES. Then they added, then they allow parallel operations. And in the next version in Kirby Lake, they'll actually have 2 engines, 2 AES engines. So basically the speed of AES is slowly accelerating over time just because Intel is devoting more and more hardware to the problem. And as AES accelerates, so will this, the graph will kind of, this line will become more flat. And as a result, we can handle more users for less cost. So over time, this system actually is going to scale really well with the performance of AES. All right, so if we use a system like this, basically we can go back to the beginning, and you can see that all the service provider sees is just, it doesn't know that Bob talks to the AIDS clinic or that the CEO of one company talks to the CEO of another company. All they see is just people talking to the Riposte server, and that's it. All right, so that's what the system will provide. And so just to summarize, to conclude, the point here is to say that in fact using very cute, very, very nice, elegant crypto tools and system design, you actually can hide very scalable systems that support lots of users and hide metadata. You can have large anonymity sets. This idea that anonymity sets have to be very small is not quite accurate these days. I wanted to mention the Talek system. This is a system developed here that also provides private pub sub systems. So again, very, very cute. I was just reading the paper on the plane up here. Very, very cute system designed here. So there's a lot of work on anonymity systems and hiding metadata. So it's a wonderful area to get involved in. So if any of you are looking for good projects to do, there's a lot more to do in this space. And so to conclude, I'll just say that kind of the problem that's really keeping us up at night is that deployment of these systems is somewhat problematic, and not because of performance, but because the complaint is that we kind of built the ultimate trolling tool, right? If you want to troll someone, now you can troll, you can kind of post nasty tweets and nasty messages, and you'll be completely anonymous. Nobody will know that it's you, so it'll be very difficult to kick you out of the system. And that's actually, again, this issue with privacy versus security, which we always try to resolve, right? I mean, in many ways, we try to get both privacy and security at the same time. Here, this is a really interesting problem. So how do we deal with this problem while maintaining user privacy? So you can start thinking about ways to maybe unmask users. So if they misbehave, maybe all of a sudden they lose their anonymity. But the minute you build a mechanism that lets users lose their anonymity, that mechanism could be abused, right? In ways you did not intend. So it's kind of I think it's a fascinating problem to come up with clever ideas for how to deal with trolling without hurting innocent users, with the privacy of innocent users. So I'll conclude with that, and thank you very much. I'll take any questions.
Thank you. We have time for a few questions. Couple questions.
Everything was clear. Awesome. That's a good sign. Yes, please.
So it seems like, for the last problem you addressed, 5 jerks can sort of ruin a single row in the table, but they have to basically attack a random user rather than a particular user.
Oh, I see. Well, they would have to know what that user chose, so there's no way for them to tell what that user chose. But if they get lucky enough, they can kind of blow away somebody's entry, but not everybody else's entries. Yeah. And so it's a matter of basically, with this coding trick, you can set the threshold to be whatever you like. Yeah. And so you can make it 10 or 15 or whatever. But they can't. They won't be able to blow up a target user. They could blow up just a random user. Yeah. That's a very good point. Right.
This is going to be vulnerable to like large Sybil attacks where you have just a bunch of people trying to dominate a single time unit by writing into the same table row in the table.
Yeah, and then they'll be able, absolutely. Then they'll be able to blow up that. If deliberately they want to blow up a particular table, then they could choose a particular table entry.
Right, but not blow up the table, but decrease the anonymity set for that time unit if you're able to like actually.
Oh no, that they can't do, right? That they won't be able to do, right? I mean, so even if you have 100 people, so the anonymity set is 1 million users, and then let's say 1,000 of them are bad, then you still won't be able to tell of the remaining ones who wrote what. Sure, if 999,000 of them 999 are bad, then the poor leftover guy loses his anonymity. But that's why we have large anonymity sets. So it's hard to control everybody. It's a very good question. Yeah. Very, very good point.
Okay, well,
Yeah, great.
let's thank Dan. Again, there's a reception in the atrium following the talk, so please come and join us. Thanks.